I'm a PhD student in the Korea laboratory in France. My supervisors are Vincent Moreau here and Ghislain Lartigue. And I'm going to present you my work, of which final aim is the simulation of a reactive fluidized bed reactor using coupled CFDDEM. So, just as the previous speaker, I won't talk about how particle-laden flows are ubiquitous in nature and in industry, just saying that they still raise numerous questions due to the many experimental issues that we are facing when dealing with industrial operating conditions. Hence the objective of promoting numerical simulations in order to get another insight into this kind of system. So today, some industrial scale simulations have already been performed using mostly Euler approach, but now we know that this type of Euler approach still needs smaller scales model in order to design some solid phase closures properly, even if now we know that the reverse is also true, thanks to our two previous speakers. So in this context, So after this short introduction, we'll reach the core of the presentation, which is mainly dealing with our numerical implementations of coupled CFDDEM in the YELS2 code, which is also developed in the Korea laboratory. As you know, we are to deal with contacts between particles, but also hydrodynamic, heat transfer, and chemical phenomena in the fluid phase that are knowing that the two phases are strongly coupled. And we will a bit focus more on our management of non-planar boundaries and massive parallelism for unstructured meshes. Then finally, we will move on to our progress towards the simulation of a semi-industrial setup. So you are now really all familiar with these three typical strategies of for modeling granular flows, ranging from the modeling of the micro scales to the macro scales, knowing also that fluidized beds are a strongly multi-scales problem where the largest features of the flow are influenced by small scales. So in this regard, we focus on a mesoscale approach that classically comes in a Eulerian Lagrangian formalism, where the fluid phase is modeled using a classical LES framework, and the solid phase is modeled using a discrete element method. So when dealing with discrete element method, you have to solve the Newton's equation of motion. It has been said previously for each particle individually. So in our case, to model the contact force, we use a soft sphere model approach that tells that globally a collision between two particles is equivalent to a damped spring that would link the two particles. So globally it says that the contact is solved over time, meaning that the particles are approaching, and instead of colliding, they overlap, and they overlap more and more until the strain of the spring is such that they have to part. So we can define many quantities during the contact, but one is of particular interest here. It's the overlapping distance between the two particles, because it will be used in our computation of the contact force. And we will see later that it's not straightforward to obtain it in some cases. So regarding the rest, I missed a few minutes to implement your approach, Jeremy. So basically, we are just using for now when and you and ergon correlations, sometimes with the help of a smoothing function. No, you didn't mean to see that, though. Regarding the heat transfer, we only use the influence of the surrounding fluid from particles. We'll talk a bit later if you want. No, I will flee probably. But then classically we use the gun correlation among others. And all of these equations are advanced using a second order Taylor scheme. So regarding the flow solver, we use the YELS2 solver previously introduced by Vincent, which is able to solve the incompressible low Mach number Navier-Stokes equations for turbulent reactive flows on unstructured meshes. I won't talk too much about this. These are the LES filtered equations for granular flows. So mass conservation equation, momentum, enthalpy, and species transport. You can see here two terms which are directly coming from the interaction with the particles. Here a momentum source term, a heat transfer term, and you can notice there are no coupling between the two phases regarding chemics. Regarding interpolation and projection steps, which are often needed in this type of simulations, we use the same weights for both operation, which are coming directly from linear interpolation. which possesses interesting moment conservation properties. our filtering operation is a bit, well, it seems a bit strange sometimes. All right, Olivier? No, it's okay for this one, right? This one is really useful for us because it's only based on direct neighbors, so it has been said that for parallelism purposes it's really interesting. So now we can figure out how we can handle this in complex geometries. So the problem we are facing here is how to deal with a collision between a particle and the wall, which is explicitly meshed. Here, as a reminder, is the computation of the normal component of the contact force, which depends on the overlapping distance between the particle and the wall, and the normal vector here in blue that we have to define. So here is taken a very simple example of a particle which is somehow overlapping with a wall that simply consists of a face F1, a face F2, and their intersecting point P. So how to deal with that? Well, the answer is that we need to know the particle's closest point, which is on the wall. And here we can start by tracing the perpendiculars through each one of these faces. And that you can notice that if the particle center is in this zone, then the closest point of the particle on the wall is actually point P. And then the numerical quantities that we need here, the overlapping distance and the normal vector, can be basically defined as this. On the other hand, if the particle is in this zone, then the closest point on the wall is actually the projection of its center on the face F1, which we called P1, and the quantity that we need can be defined as this. And finally, if the particle is in this zone, then this is equivalent. The closest point on the wall is the projection of its center on the face, and the quantities that we need are this one. So basically what we are saying this is that we are unveiling the basic concepts of Voronoi region, which have been a bit talked about here. Here you can see the Voronoi region of the face F1 in green, of the face F2 in blue, and the Voronoi region of the point P in blue here. Oh, it was red, sorry. And that concept can be extended in 3D. So here you can see an example of a Voronoi region of a vertex, of an edge here, and of a face. So now the question has become, in which Voronoi region my particle can be located in. So in this regard, what we do in the code is that we store all the faces normal of all Voronoi regions of all boundary features in order to compute some dot products to identify in which Voronoi region is any particle. And with that method, we can compute the closest point and then obtain our contact force. The problem with that is that a priori, any particle can collide any number and any type of boundary feature at the time simultaneously. And boundary features here are can be faces, edges, and nodes, thus requiring as much distance computation or dot products computation, while in fact hardly a few boundary features are collided by a same particle at a given instant. Hence, our solution to discard more and more operations, obviously, in order to improve the numerical cost of all these operations. So here is an extension of the 1D case I've shown you just before. So basically what we have to do is first to identify the particles that are located very near the wall. And to do that, you can simply identify the mesh cells that are very close to the wall. And in fact, you can start by this statement that the cells that you need to identify are finally those that are within a particle radius from the wall and nothing more. So what we do is that we use an analytical distance to provide, analytical method, sorry, to provide any interior mesh node to the wall distance in an analytical fashion. So here you can see a near wall region for the processor number 1, a physical boundary here in red, our distance instruction here, which is a particle radius. And so this method allows to step by step identify only the cells that we need and nothing more. And this method is fully compatible with any mesh element types and any kind of parallelism we have to deal with. So now that we are able to identify the mesh cells and thus the particles that are very close to the wall, we have to know in which zone any particle can collide. We are looking for some local information here. So what we do is that we are able to decompose the boundary into small groups of contiguous faces for which we define and store some bounding a bounding sphere for this group, and then for each one of these groups, we also store the bounding spheres of each faces individually. And thus, in the end, a particle will first test its intersection with the bounding sphere, of the groups, and then, in case of intersection, it will test its intersection with the bounding sphere of the individual faces. And finally, here there's a third test, which in this case is not useful, obviously, on the overlapping distance. Well, just the thing is just to know whether the particle overlaps the planes defined by the faces or not. And in the end, we can afford the price of this operation, so the Voronoi regions belonging test, of which I was talking to you just a few minutes ago. And finally, to identify the closest point and to compute the normal contact force. So we can just illustrate this on the very simple case of a silo discharge, which can be described by the Beverly law that predicts that the solid mass flow rate at the outlet here, W, is independent from the solid height inside the silo. It can be written as this. It can also be written as this for plotting purposes. So we did this run on an hourglass. Here are presented 6 simulations for 6 different particle diameter. And you can see that for these sets of parameters that are quite consistent compared to what we can find in the literature, we obtain a good tendency. Now we have to deal with the problem of parallelism management. Here again, some performances issue, because each time your particles are time advanced, they need some updates with the neighboring processors, and that may include many processors and involve many numerous messages of potentially big sizes, and you have to do it twice per particle time step if you are using a second order Taylor scheme. So here again, the solution is simple. We want to reduce the number of messages, their sizes, and if possible in an asynchronous fashion. So here is taking the example of a cylindrical part of a simulation domain, a mesh with tetrahedron. Here, one color stands for one processor domain, and we are interested in the processor 1 here. So what we have to do is to, again, define a cell halo around the processor 1 domain in order to identify the only necessary particle without identifying particles that are too far. These one will be the ghost particles that will be sent by the other processors to processor 1, and we have to deal with unstructured meshes still. So we are facing exactly the same problem as before concerning the halo size, but unfortunately we couldn't use the same method using, with the Voronoi region because of the lack of adapted structure, so that's a purely numerical problem. And also that the quantity of processors interface can be much greater than the quantity of boundary, so this could raise some memory problem. So what we do is, again, with this statement that we don't need to identify more than the particles that are really close to the processor's interface, we use a fast matching-like algorithm that looks a bit like the one that are used for level set methods. That uses markers to map the processor's interface in this fashion. Here you can see a processor's interface in red, our distance instruction, and here again by mapping the processor's interface with markers and propagating this distance more and more, we are still able to identify exactly the number of cells that we need. And again, this method is fully compatible with any mesh element type, and also compatible with parallelism, in particular when we have to cross some other processor's interface, and that's not straightforward. Regarding our communications management, so once we have defined the cell halo around our processor 1, we can take a closer look at the interface between processor 1 and processor 6. Here you can see some particles on processor 6, and you can notice that some of them are within the cell halo we just defined. So what processor 6 does is that it groups all these particles, and then it packs only the necessary data useful for to compute the contact force in one unique type, real type array, which is exchanges in a non-blocking fashion to processor 1, and then processor 1 just has to unpack it to create its own ghost groups, and then it does exactly the same for all of these neighbors. And so finally, we could really reduce the number of messages, their sizes, and minimize the blocking that can occur. So here, a few results. Here is a weak scaling of the YELS2 code in a very simple case. This is a box with planar boundaries meshed with hexahedrons. So this is really simple. It's quite satisfactory. You can see here that the last point stands for a simulation gathering 800 million particles on 200 million hexahedrons. Here is a more realistic case. It's the strong scaling of the code on the gas fluidized bed, which is experimented in the University of Birmingham. We will talk about this a bit more later. It's filled with 10 million particles and 30 million tetrahedron, and of course, because of the cylindrical part, it's meshed with tetrahedra. Here again, the results are quite satisfactory. Some timers here, we could notice that the MPI communications in all of these cases represented less than 12% of the total CPU cost, and the complex boundaries management represented less than 4% of the total CPU cost management. That was a good validation for our numerical methodology. But yeah, you guys know that particles are really costly in CFDDEM computations, and you know that it's really difficult to achieve a good scaling of DEM codes because for the greatest part the mesh algorithm the mesh partitioning algorithm they don't take the presence of the particle into account. So here on a very simple case, you can see that for a bunch of particles at the very bottom of this cylindrical part, that mesh partitioning is proposed by a classical algorithm. But we would prefer something like this, where the particle phase is dispatched between 3 processors rather than 1, obviously. And what we could notice when we first run the fluidized bed of the Birmingham University, we could notice that in any case, almost 60% of the processors were perfectly empty from particles. Although we would like something like this, where the processors are more numerous, where there are more particles. So how can we achieve this? Well, this is the Birmingham fluidized bed. The fluid fraction is shown on the left, and the vertical gas velocity on the right. And what we do is that we extract during the simulation, so in a dynamic fashion, we extract the bed height that we are able to calculate in some fashion. And then starting from the initial mesh partitioning, and regarding this bed height, we are able to instruct a proportion of processors that we need to have under the bed height and above the bed height. And finally, we are able to achieve something like this. And there is a second part in this dynamic algorithm, is that it is able to judge whether load balancing is necessary or not, using some criterion. And also the local dispersion of particle here is also taken into account, so that the processors inside the bed height are dispatched regarding the particle localization. So here are shown the results. Here is plotted the physical time that we were able to reach over 24-hour simulation for still the Birmingham case. So without load balancing in red and with load balancing in blue. So basically you can see that in the first zone here, the simulation run 2 times faster, and in this zone it run 1.5 faster only because as the number of processors increases, the number of degrees of freedom of the load balancing algorithm decreases, and so it's much more difficult. And these operations represent less than 5% of the total CPU cost. So why so much optimization? Well, I've just told you about the Birmingham fluidized bed that contains 10 million particles, but the one that I should be able to tell you about is that one. That's the final object of our study. and it contains 200 million particles. The problem is that because we use some soft sphere model and something like this, in fact, what we found is that the time step we should use in the second case is a third of the time step in the first case. And then the total particle cost should be multiplied by 60 theoretically. And obviously, we know that it's of particular importance because we only have 3 weeks to run our simulation, and so, yeah, we have to deal with it. So, the final object is this one. So this is the reactive fluidized bed, which is experimented in the LGC laboratory in Toulouse in France. It consists of an almost 2 meters high fluidized bed, which is filled with chemically inert sand particles and fed with a mixture of natural gas and air. Here, many sensors are present on the center line of the reactor, and the interesting thing, there is a cooling air system at the bottom of the reactor that somewhat allowed to control the global bed temperature at the bottom here. And what they noticed is plotted here. So here is plotted the temperature measured by the sensor minus the global temperature they were able to control at the bottom. So you can notice that for the lower values of this global bed temperature they could measure, what happens inside is that the temperature measured by the sensors is increasing above the bed. And that means that the combustion of methane occurs outside the bed, above the particle phase. Whereas for high values of the global bed temperature, the temperature decreases above the bed, meaning that the combustion of methane occurs inside the bed among the particles. So that exhibits the existence of a critical bed temperature under and above which the combustion regime is completely different. And that critical bed temperature should be between around 700 degrees and 850 degrees, and that's what we are interested in. So regarding our modeling strategy, as introduced by Vincent, we should use, in the first place, a dynamic thickening flame front technique in order to ensure a sufficient mesh resolution for our flame front. So basically, we just thicken it while preserving a good propagation speed. The kinetic scheme is really simple, elementary, only a two-step mechanism for 6 transported species, and definitely we needed to validate this modeling strategy on a very simple case. So this case is presented here. So it consists in a 25 centimeters high cylinder filled with almost 2 million particles, and here the colors are stand for the mass fraction of CH4 in the gaseous phase. So we run a simulation at 700 degrees, so just under the critical bed temperature we want to find, and at 850 degrees, so just above the critical bed temperature we want to find. And you can clearly notice here that for the lower bed temperature, the conversion of methane clearly appears outside the bed, while on the contrary, for the higher bed temperature, the conversion of methane occurs also inside the bed. And this is confirmed in this video that was taken for the case at 700 degrees, where you can see clearly that a flame front is propagating above the fluidized bed without entering it at all. So that confirmed qualitatively that we want to find the critical bed temperature we want to find. So these are only preliminary and qualitative results because we have no experimental values on this fake smaller case. So here are just shown on the center line of the reactor, the temperature and the profile for the main species. So we can just imagine here that we are really facing a shift in the combustion regime because of the existence of this critical bed temperature, which is between 700 degrees and 850 degrees. And here is just quoted the chemical source term of the CH4 species regarding the fluid fraction, and you can really see that the combustion regime is not the same. In the second case, we are mostly burning in void bubbles, but also in dense, rather dense region, which is quite interesting. And so These are the very first instant of the simulation of the LGC fluidized bed. So we have they're containing 200 million particles and running on 2,000 cores, and we definitely have to test our modeling strategy for combustion purposes in this case. So hopefully we'll get some results next time we meet. Thanks for your attention.